All right, today, big day. So the concept today, this has some like far-reaching implications. The concept that we'll talk about today will be used this chapter, next chapter, and the chapter after that. Okay, so like big day to pay attention, bring your A game. Okay, so I'm going to start with a disclaimer. So I try really hard in this class to teach things that are applicable to your life. Like I want to be able to answer the question, when am I ever going to use this in life? Like I should have an answer. Like it's not saying that your career is going to be based upon this, but like there's evidence of like, oh yeah, okay, yeah, I can see how that plays out. Okay, so electric potential at a college level is can get really theoretical, can get really mathy. And what I've done is filtered out all like a lot of the theoretical stuff and a lot of the math stuff just to get at the heart of like here's why it matters. And so what I've done is saying we're just going to look at electrons. Electrons are really what matter. They're the things that are moving and do stuff. So we're just looking at the electrons. If you try to communicate this lesson to a college professor, they'd be like, what is your teacher on? Like, this is not physics. There's a whole side of things because I'm ignoring the protons on the positive side. There's a whole math side that we're just kind of like, you'll get to later. And I'm going to get at the heart of like conceptually what this is. If you take physics later on, and you can pick up the math later. Okay, so that's my disclaimer. Here we go. Thumbs up when you have a guess. Tell your neighbor. Correct answer is A is the correct answer. Okay. The way that I think about it, let's pretend that there's a compression spring between the two. They want to repel, and so you're squishing them together. Where's there more potential energy? There's a lot of energy there versus here, because they want to go. Good at that. Okay, so this lesson, these diagrams, the dots represent electrons. Okay, and you can kind of pretend like there's compression springs between each of the electrons. Okay, I want to know which arrangement has more potential energy, like a total potential energy. Adding up all the springs' potential energy. Thumbs up when you have a guess. Tell your neighbor. Correct answer is B. Because there are more springs. Okay? Because with that, like you add up all like you're just collectively there's more springs, same closeness together. So there's more energy here than there is there. Okay with that? Follow-up question. Same scenario. Thumbs up when you have a guess. Have a conversation. Okay, correct answer is C. Okay. So electric potential is how much electric potential energy there is technically per charge, per amount of charge. It's in units of joules per coulomb. When I was in your shoes, that made 0 sense to me. I'm like, okay, I'm gonna jump to eggs. Okay, what this is saying is how much energy there is per dozen. But at a very foundational level, it's talking about how much energy per egg. So taking away the analogy, it's how much energy there is per electron, rather than per joule, which is a large quantity of extra electrons. It's how much energy there is per electron. And how do you know that from this? You're looking at the electron crowdedness, how closely packed they are together. Okay, each electron has 4 springs connected to it, and they're equally squished. This electron has just as much energy as that electron does because they're equally squished. You okay with that? Okay, good. Okay, so I apologize from the physics community at large that we called things really close to the same, like different concepts, but similar names. Like you got electric potential energy and electric potential. I was like, really? Like could have like expanded, like branched out a little bit on the names here, but it is what it is. Okay. So what is electric potential? Electron crowdedness, how much energy there is per electron. Okay. Now, this description that I'm going to give you right now, a physics professor would make them happy. Like, okay, he does know what he's talking about. You don't need to know this. I'm just letting you know, just to like round it out. So you know the relationship between electric field and electric force. Like the electric field is the promise of an electric force. Like if you take something with charge, and you stick it in to the field experiences a force. So electric field is the promise of an electric force. Electric potential is the promise of electric potential energy in that same relationship. Okay, so like you have electric potential here. There's the promise of electric potential energy. If you take something with charge and you stick it at this location, it's going to have a certain amount of electric potential energy. So you don't need to know that for this class. That is just, okay, moving on. Thumbs up when you have a guess. Tell your neighbor. Correct answer is? Correct answer is A. Because the electrons are really squished together. The springs between them are super compressed. There's a lot of energy per electron. Good with that? Same scenario, different question. Yeah. Mm-hmm. So we collectively add all those together and then divide them by how many electrons there are. Does that make sense? Good question. Have a conversation. Okay, here's what I'm going for on this one. B is what I'm going for. Yes, it is possible. Okay, I'm going to make an analogy using money. Okay, so electric potential is how much energy there is per electron. Okay, so I'm going to use, instead of energy, I'm going to use money. So I'm going to say here, each electron has $1,000. Super crammed together. Here, each electron has $100. So when you add all those up, you get maybe like $10,000. Is it possible that you have enough electrons that each have $100 to have the total amount of money that's more than $10,000? Sure. If you get enough electrons, at some point, they're going to add up to have more than $10,000 than that. All right with that? But each electron here is richer than here. But collectively, there might be more money. All right with that? Okay. Thank you. Oh, sorry, correct answer is B. Bountiful buffaloes. Yes. If they're equally crowded, then you would say A. Yep. Okay. Good with that? Okay. So, variable for electric potential, capital V. The variable for electric potential difference is delta, capital V. What do you know? Because we say delta, mathematically, what do you need to do for the electric potential difference? Final minus initial. You are subtracting things. You are finding the difference between two things. So electric potential difference is the difference in electric potential. Because we're just focused on electrons, I'm going to put the absolute value because I don't care about protons and stuff. We're just, it looks more complicated, but this is actually making your life easier. Okay, it's the difference in electric potential. So tell your neighbor how you would make this quantity bigger. What would you do using this equation to make this side big? Okay, this one's kind of hard to not use the word difference. Like you use the word in the, like, how do you make electric potential difference bigger? Well, you make the difference in electric potential bigger. You make when there is a larger contrast in V1 and V2, or V2 and V1. Okay, on a number line, they're farther apart. Those measurements are farther apart from each other. Good with that? Okay. So object 1 and 2 have the same electron crowdedness, same electron density. Three is more spread out than 1 and 2. Tell your neighbor. Correct answer is? Correct answer is C. There's a bigger contrast in crowdedness between 3 and 4 than compared to 4 and 1 and 4, sorry, 4 and 2 and 4 and 1. Hang on to that thought. It's coming to you. But do you see the, like, there's a bigger difference in crowdedness here compared to here. To that. So there's a larger electric potential difference from here to here than from here to there. Thumbs up when you have a guess. Have a conversation.
Well, I need 59. I don't know what it's on this spreadsheet. In my spreadsheet. What is that?
Correct answer is? Correct answer is D. Dangerous dinosaurs. Okay. The difference in crowdedness is the same between 4 and 1, 4 and 2, and 4 and 3. Because 4 is obviously the same. And then 1, 2, and 3 all have the same electron density. Okay. So why am I teaching you about dots? Like, where do you, like, okay, I'm figuring out this puzzle, but like, how does this correspond to life? Have you heard of the word voltage? Next chapter.
What's next chapter?
We'll get there. Okay. Electric potential difference is the same thing as voltage. They are one and the same. There's two different words to describe the same thing. Okay. This is the concept that is going to take us, it's going to be in this chapter, next chapter, and the chapter after that. Okay. Has far reaching implications. Here's the killer. You've heard this word before. So you've come up with some idea of what it means and what, but some of that's wrong. Okay. No. And so part of my job today is to try to give you a better understanding of what voltage is and what it is not. Okay. So another way, another math or another equation to describe electric potential difference is the amount of potential energy that's transferred over how much charge is transferred. So like if something gets shocked, how many electrons are being taken the jump versus how much energy is being transferred in that jump. Okay. So you got that equation. So here's how this is manifested in real life. Okay. So electric potential difference or voltage, that determines how motivated the electrons are to transfer, to jump, to shock. Okay. Electrons, if you remember, are always interested in going to a better environment. They will always want to go to a better ratio, right? Okay. So if you were If you were an electron, where would you rather be? In 4 or in 2? If you're an electron, where would you rather be? In 2 or in 4? Those are your choices, 4 and 2. Where would you rather be? 2. Spread out more, right? If you could be in 4 or 3, where would you rather be? 3, right? Where is there a bigger difference? 4 to 2 or 4 to 3? 4 to 3, right? So the electrons in here are more motivated to go to here than they are to go to here. Does that make sense? There's a higher electric potential difference in crowd. There's a higher electron crowdedness difference in electron crowdedness here and here versus here and here. They're highly motivated, higher motivated to go from here than they are to here. Good with that? So voltage describes the motivation or the desire for electrons to transfer. Okay. Now, at the end of the day, what really matters is this shock going to hurt? Is it going to cause damage? Is it going to destroy something? Is it going to put someone in the hospital? Is it safe or is it dangerous? This, how much energy is transferred, is what we need to measure, what we need to be aware of, what we need to like watch out for. Like if you have too much energy being transferred, that's when it's going to kill somebody. Okay, so looking at this equation that I just gave you, what's going to cause your potential energy transferred to increase mathematically? What's going to cause your potential energy transferred to increase? Tell your neighbor.
What? Like you isolate
Okay, check this out. Mathematically, I'm going to rearrange this. Is everybody okay with what I just did there mathematically? Okay. The answer is I could increase one or both of these. I could make the voltage, the electric potential difference, larger. That would increase that. I could also make the amount of charge transferred, the amount of electrons transferred, larger, both of which would cause this to increase. You all right with that? So like and or an increase of both of these or one or the other would both cause that to increase your potential energy. Good with that? Tell your neighbor. Okay. What am I asking for? What would be another way to ask this? What pair is more likely to get shocked? What measurement am I comparing? I'm looking for how motivated electrons. I'm looking for voltage. Which one has a greater electric potential difference? C. Comparison of crowdedness. Electrons are more readily to jump here than they are here. Good with that? Okay. Thumbs up when you have a guess. Have a conversation. Okay, what do you say? Correct answer is B. Beautiful butterflies. Okay. Now, D has an electric potential equal to 0. That would be no electrons. If this said electric potential difference of 0, that would be correct as well. Okay. They're going to transfer until, like, why would I want to go over there? They're just as crowded over there as they are in here. Like, the difference would be 0. There would be no motivation. They'd have the same crowdedness from one spot compared to the next. You okay with that? Thumbs up when you have a guess. Okay, I'm going to talk you through this one. Okay, so we're all good with the fact that it's going to go out of 4 into the other one. Okay, but let's check this one out. So one electron jumps over, another one jumps over, another one jumps over, another one jumps over. At that point, I would think that those two scenarios, places would look the same crowdedness. You okay with that? So at that point, they're done transferring. Okay. what I'm looking at is this. So they both have the same voltage, but what I'm trying to figure out is which is going to transfer more energy. And what's going to determine that is how many electrons are making the jump, because the voltage comparison of crowdedness between 1 and 4 and 2 and 4 are identical. So this is the same. But I'm looking at which one's going to have more electrons jump. Here we had 4 electrons jump. Here, if we put 4 electrons in here, would there still be a desire for electrons in here to go over there? Yeah. Like, oh man, there's still some room because this space is bigger. Does that make sense? So this shock is going to hurt more because more electrons are actually transferred because there's more room to spread out here. Even though their electric potential difference was the same. You ready with that? Okay. So let's bring it home, not talk about dots. Let's talk about real life. Okay. In an outlet, see that? In an outlet, does anybody know the voltage, the electric potential difference from one prong to the next? Yep, depending on who you talk to, they'll say 110 volts or 120 volts. Okay, so there's electric potential difference, a difference in crowdedness from one prong to the next. They're that motivated. Okay, have you ever seen warning signs on those electrical playgrounds? It's the ones that are like wired off and they're like, don't climb in here, but man, they look so much fun. Like the jungle gym. Yeah, high voltage. Warning. How many thousands of volts? I've seen 5,000, I've seen 10,000, I've seen 20,000. Okay. 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 So when this
What is the sticker? What is that?
It's the emperor.
Oh, that's not I thought it was a cat.
Okay. When this is charged, okay, when this is charged, real quick review, we'll say roughly around 100 volts, 120 volts, 110 volts. Caution, warning, 5,000 volts, 10,000, 20,000 volts. When this is charged, the electric potential difference between this and me is around 100,000 volts. 100,000 volts. Mr. Smiley, why do you have this in a school? Like, that could, like, kill you? I touched that the other day. Okay, so what I'm going to try to show you is what voltage is and what it is not. Okay, When you plug something in, are you safe? I mean, we trust this all the time. As long as you don't touch the metal, as long as you grab hold of the cord part, you're good, right? That insulation protects you from being shocked. Good with that? Okay. Now, what I'm going to do, I've cut a cord.
Cutting a cord is never a good idea.
Okay. So what I'm going to do is I'm going to take this cord and I'm going to plug it into the Van der Graaf generator. A little sketchy, but I'm going to tape it. Okay. Okay. So the question is, am I going to be safe from being shocked? Okay, so I'm going to turn this on. Where's my on switch here? Okay. Can I see that? Okay. Was I being shocked? Yes. Did you see the sparks?
Yes.
Okay. I was being shocked. Now, I didn't die, but did this. Here come the lights. Did this cord, did this insulation protect me from being shocked? No. Why not? Because the electrons in here were so packed in there, so crammed together. There is so much energy per electron that they look at this insulation and they scoff at it. Like, are you kidding me? I'm so through that. Like I'm just gonna, oh man, just spread out like and it has enough motivation to jump through this insulation to me, to spread out. You good with that? That's what voltage is how motivated the electrons are to jump. Super crazy motivated. Okay? In an outlet, I'm fine. It's only 120 volts. They're not that motivated. There are electrons in there, sure are. They're crowded. They'd rather be in me, but they don't have enough energy per electron to make it through. Okay? So here's a follow-up experiment. Don't do this at home. Okay. What I'm going to do, I'm going to
Oh, that.
just a ball.
You have like a ball of oh, good. It's got the protective glass now. I don't know if that's better than.
Okay. What I've got, it is some steel wool. Okay. And I'm going to I'm going to shock this with, I took that off already. I'm going to take this and I'm going to shock this with the Van der Graaf generator, the steel wool. Okay. How much time do I have left?
Much time? 10 minutes.
Okay, we're good. We're good. Okay, so I'm gonna take this and I'll plug this in across here. Ready? Nothing. It was shocking it, but okay. Now, this is the part. Don't do this at home. Okay, I'm gonna plug this cut cord. Okay, and I'm gonna touch it to both sides, like either side of the steel wool. Okay, it's super sketchy. Don't do this. Okay, don't look directly at the steel wool. Look at my face. 3, 2, 1. Okay, we're safe. All right. All right. Now, here's the deal. 120 volts destroyed, incinerated the steel wool. 100,000 volts didn't touch it. 100,000 volts. 120 volts. Okay? Here's the deal. It has to do with this equation. Okay? The Van de Graaff generator, it had a large voltage, but the amount of electrons on here that transferred weren't that many. And so it didn't make that big of a, it didn't do damage. That's why we're safe. You can feel it, but it doesn't put you in the hospital. Okay? The outlet had a small potential difference, but the amount of charge that was transferred was huge. And so it causes a lot more energy to be transferred. Okay? You all right with that? There's just, in the outlet, there's just an endless supply of electrons. They're able to be transferred. Okay? Here's an analogy, a money analogy. So electric potential is how much energy per electron. I'm going to say, let's change energy to money. Okay? Kuwait. It's a small Middle Eastern country. It's oil rich. Okay? Each person that lives in Kuwait is like a billionaire. Okay? They're loaded. But Kuwait doesn't have that much influence on the global economy because it's not that big of a country. There's not that many people. There's not total amount of money. Okay? This is like Kuwait. Okay? China, on the other hand, has a lot of global impact. Okay? But if you look at how much money there is per person, not much. But, okay, China is like the outlet. Okay? There's not that much money per person, but there's so many. It's huge that they can do stuff and destroy the steel wool. Does that make sense? Okay. So there you go. What voltage is, what it is not.